I was asked in office hours if I could do an example problem that would include conservation of energy and rotation. So here's an example problem. Let's say we've got a hoop up here, and that means it doesn't have any mass in the middle. It's only got mass on the rim, and it's raised by a height of h on some ramp. And we release it from rest, and it rolls all the way down to the bottom, and what we want to know is what's the velocity of this thing at the bottom. So this is a conservation of energy problem. And you can think about the initial energy, and it must equal the final energy there. If the hoop is up at the top and it's not moving, then we know that the only energy it has is mgh. That's gravitational potential energy. Now, if it's rolling at the bottom, it must have no more potential energy because it's gone all the way down to the bottom. It has no more height, but it will have kinetic energy, 1/2 mv squared. So that's kinetic energy due to translation. And then it's going to have rotational kinetic energy, 1/2, and instead of m, we have I, and instead of v, we have omega squared, like this. So this is our equation, like that. And what we want to do is solve for v bottom. So we want to find the velocity at the bottom, which would be this v right here. So let's expand things a little bit more. This I is the moment of inertia, and for a hoop, it's just m times r squared. So that's the moment of inertia for the hoop. And so I can still write it like this, 1/2 mv squared plus 1/2 mr squared times omega squared, and that's equal to mgh. And to simplify things, I can get rid of the m's, like that. So I can say gh equals v squared over 2 plus v squared, or r squared, sorry, r squared over 2 times omega squared, like that. Now, I want to simplify this even a little bit more. And the typical problem that you have with combining rotational things, which would be this term that has the omega in it, and linear things is this term has a v in it. So what you want to be sure of is that you have this little way of relating linear velocity, v, is equal to the radius times omega. So that's going to help us. So what we're going to do is basically say, I want to sub out omega. And so in order to do that, I can basically say velocity divided by radius is equal to omega. So now I'm going to take this line down here and rewrite it as g times h equals v squared over 2 plus r squared over 2 times omega squared. And omega squared is going to be v over r quantity squared. So then I get r squared v squared all over 2r squared plus v squared over 2 equals g times h. And here you can see that the r squareds will cancel, and so I get gh equals v squared over 2 plus v squared over 2. So gh equals v squared, and so square root of gh is going to equal v. So that's your answer. And again, just to summarize, you do conservation of energy. So we're looking at the initial energy and comparing it to the final energy. And you must include both translational kinetic energy and rotational kinetic energy. And when you simplify these equations, you're still stuck with this sort of issue, that you get v in one location and you've got omega in another location. And you must use an equation like this to translate and put them all in terms of one variable. So in this example, we did it for v, and that's the answer. Hope this was helpful.